Okay, so good morning. Okay, welcome back after your recess week. All right. So yesterday I walked around the lab. All right, and I saw some of you. For some reason, when you try to load the OS, okay, for some of the boards, it works fine with some of your PCs, and for some of you, it always has some fault or some error, and you can't run the program. All right. So you try to experiment with the version control of the CMSIS drivers or RTX and see if that helps. Okay, if it still doesn't help, we will try to see what we can do. Okay, but as long as maybe one or two members in your group can get it to work, then you manage with that first. Okay, we are still trying to see what is the issue and why some of your systems cannot work with the RTX loaded. Okay, so we will look into it, but in the meantime, as long as one or two members in your team can get it to work, then it's fine. So you can still work on the code, but you test on those systems where it works. Okay, so let's recap what we saw last week. So last week, the week before last, when we first got introduced to the OS, all right. So basically what we saw was that I now have the ability to create multiple threads. Okay, so in our case, we have the LED red thread, okay, and we have the LED green thread, okay, which we saw last week. And once I create multiple threads or multiple tasks, okay, they run sort of independently, okay, within their own memory space. Okay, so they have their own variables, their own stack, okay, and they manage the resources that they need. Okay, and at the same time, okay, while they are running, okay, two things can happen. Correct. One is, of course, you may call some OS. You may make an OS kernel call like OS delay, which will force you to go into some sort of a block state or wait state. All right. So that is one thing that can happen where you give up the processor and you allow another task to run. Okay, so if I call OS delay, okay, that allows a context switch to happen. All right, but at the same time, okay, even if I don't call OS delay, okay, if I call a normal delay function, okay, my normal delay function, then it is still possible to have a context switch because of the round-robin nature of the RTX. Okay, so you can always switch between tasks when one task voluntarily gives up the CPU, like in a case of OS delay, or through the round-robin nature. Okay, so that is what we left off before we went for the break. All right, so from now already you see that the way we have to think about designing the whole system and the architecture will change. Okay, because up till now we are very used to having what we call a super loop. Okay, so we have a while loop. Okay, and inside that while loop we have task 1, task 2, task 3, task 4, and so on. And then we have interrupt 1, interrupt 2. Okay, at the same time we have hardware enable blocks like PWM and so on. Okay, so until now we have been thinking in this mode of operation. Okay, so we have a while loop, okay, and for some immediate response we have interrupt, okay, and we can make use of hardware blocks like UART or PWM to generate some signals along the way. Okay, now we can still have all of that, but at the same time now we change the whole architecture of how the code is designed, that instead of saying I run task 1, task 2, task 3, task 4 in sequence, I am now going to say that each of it is now a task. Okay, task 1, task 2, task 3, task 4, each of it is now a independent task that is going to handle something for me. Okay, so one of it can handle motor control, one of it can handle LED control, one of it can handle UART interface, okay, one of it can handle audio. Okay, so now instead of thinking sequentially, you think of everything in parallel. Correct? Everything in parallel. Okay? So now, when we go in this direction, okay, where we say that everything can happen concurrently, it leads to another challenge, correct? How do I synchronize? Okay, because when I do sequentially, that ensures that everything goes in a flow, correct? I do activity 1, activity 2, activity 3 and so on. But now when I say everything is concurrent, then how do I synchronize the behavior? How do I ensure that when the motor stops, then the LED turn on, correct? Or when the audio is playing, then the LED will change behavior. How do I communicate between different tasks? How do I synchronize the behavior and so on? Okay, so that is what we're going to look at for this week and next week. Okay, so the first thing we're going to look at is the idea of concurrency and how do we manage our resources when everything is concurrent. Okay, so before that, just a quick recap on the project. Okay, so from the video that I showed before, you would have seen the setup. Okay, so that setup was in the DSA lab. Okay, we will have a similar setup outside the makers. Okay, right outside the makers, where we were near the where the water cooler is, near the COM3 and PH. Okay, so that is where the starting point will be. So the water cooler will be somewhere around here. Okay, and then we will set up this. Okay, so the dimension, all don't worry, we will finalize the dimension and tell you all. Okay, so basically it will be the same flow. That means there will be a straight path that you need to go. Then there will be a ramp. Okay, and after the ramp there will be some cones. Okay, where you need to go around, go through, and so on. Okay, and then there will be another ramp when you come back. Okay, and then there will be a few more cones for you to maneuver through, and then finally there will be an end point. Okay, so the sort of the layout that or the challenge that you need to cover is the same. Okay, as what you saw in the video. Okay, only thing that's the DSA lab, and we will do something similar outside the makerspace. Alright, now the most challenging part of this is the ramp. Okay, so the ramp is already there in the makers lab. It's dismantled, it's 3 parts. Okay, so once your robot is ready, you can just assemble it on your own. Okay, and you can test it out. Okay, now why is this the most dangerous place? A part of the whole maze is because while the robot is going up, it always very likes to fall out. Okay, and once it falls out, anything can happen. Your board can break, your wheel will come out, your wires will come out, everything can happen. Okay, so it's very, very important that when you are testing, you always have some of your team members stand by at the side to catch the robot in case it's going to fall. Don't take video until happy until you fall, then still go and zoom in when you fall. Too late already. Okay, so make sure you try to catch it before it falls. Okay, because really once it falls, anything can happen. Your board can break also, the whole chassis can break. Okay, and wires will come on and things like that. Alright, so be very careful when you're testing on the maze. Okay, so this is the only part you need to be very mindful about. Okay, the rest of it on the flat terrain is fine. Okay, going up and down the slope is the tricky part. Okay, so it's already there in the maker's lab. Okay, you just can set it up, okay, outside and test it, okay, once your robot is ready to move. Okay, so this is for you to be prepared. Okay, so the assessment is going to come soon. Which week is it? The project assessment. Which week is it? Do you remember? Where's the schedule? Let me check the schedule again. Okay, it's supposed to be in week 11, alright? Week 11. That means the 5th week of 1st April to 5th April. Okay, which basically means you have 1 month or less than 1 month left. Alright, so make sure if your Ziploc bag is still collecting dust somewhere in your room, go and take it out. Start to put things together. Alright, and start preparing. So very fast the time will pass. Okay, so within 1 month you have your assessment, which means that this next 2 weeks is very important for you to learn the overall framework, and then whatever device driver that you have developed in the first half will all have to be brought in. Okay, so like I said, whatever you did in the first half is all the building blocks, correct? Everything is there already now. Okay, so you already have your device driver for motor control, audio, UART, LED, everything is there, correct? So now this week and next week, when you learn all the different ways of designing architecture, you decide what you want to use and then you put everything together. Okay, and then everything will be working well. Okay, so let's go through this. So what is multiprocessing? Okay, so there are a few different ways in which you can have your architecture. Okay, so a very simple system would be a single instruction, single data. Alright, so that is a very simplistic, very basic microcontroller operation. Okay, so that is SISD. Then the other one is multiple instruction and single data stream. That means I take one piece of data, but I'm able to perform multiple instructions on it at the same time. Okay, so that is another hardware design. Okay, the other third option is SIMD, single instruction, multiple data. That means I perform the same instruction on a lot of data at the same time. Alright, and the last one is multiple instruction, multiple data. Okay, so all of these are very much related to the hardware resources you have within the processor space. Okay, so it depends on what kind of hardware you choose and what are the resources available to you. Okay, so again, these are some of the simple options that you have, and you can decide if you are going to explore some of the hardware options available for multiprocessing. Okay, so in our case, okay, we are using a single instruction with a single core, correct, with the KL25Z, but we are achieving concurrency, okay, through the OS. So the OS is helping us achieve that concurrency. Okay, but at the same time, we can use hardware to achieve concurrency, which is also what is happening, correct? When you say that you configure your PWM module, once it's configured, it just generates for you. Okay, you don't need to go back and do anything. So that is concurrency at a hardware level. Okay, so in our case, we are talking about operating systems on single processors. Alright, towards the last few weeks, we will look at operating system on the dual core system. Alright, on the ESP32. Okay, so single thread versus multi-threaded. Okay, now again, we need to look at communication issues. How can multiple threads talk to each other? So that is one thing that we will focus on. And at the same time, memory access, or what we call access to shared resources. Okay, in a single threaded system, if I have a memory element that I want to access or a resource that I want to access, you sort of control the access in a sequential way. Alright, the only exception to this, is when you have interrupt. Okay, the only exception to this is when you have interrupt. Okay, because if you have a global variable that is shared between your main code and interrupt, then you also need to make sure that that part is handled. Okay, but besides that, you don't have anything much to worry about. But in multi-threaded applications, anytime context switch can happen. Okay, which means that I can be working on some piece of data, and before I finish, I may be context switched out. Alright, and some other thread might come in and want to work on the same piece of data. Okay, so these are issues we need to deal with. Alright, so the issue, okay, or the challenge that we will face is what we call a race condition. Okay, where we have different processors trying to access a shared resource, and the result of the computation, okay, may depend on the exact way the processors interleave. Alright, and the race condition undermines the correctness of any system. Alright, so to give you an example, okay, so let's say I have task 1, okay, that is supposed to, task 1 and task 2. Okay, and task 1 is running and is supposed to access a block of maybe 1,000 bytes array. Okay, it's supposed to access a 1000 bytes array, and it's supposed to do some processing with it. Okay? When task 2 runs, it also is supposed to access the same 1000 bytes array and do another step in the processing. Okay? But what happens if while I'm in the midst of my processing, halfway through I context switch out? Correct? Because we have round robin, okay, or some other event can happen and I context switch out, and task 2 which was waiting, it starts to run and it tries to access the same array. So you call this num array. Okay, and I access the same num array here. Okay, what happens when task 2 tries to access this block of data? Half of it is new data, half of it is still unprocessed. Alright, and it may not be aware of that, and it just continues to do it. Alright, and then when I finish and then I go back, eventually, then what happens? Then I'm also dealing with some data that has been updated by task 2, some data that has not been updated by task 2, that is not finished by task 1. Correct? So again, it can mess up the correctness of data. Okay? And it's very easy to make this kind of mistake if you don't handle the access to shared resource correctly in a multi-threaded environment. Okay, so that is why this is very, very important. Okay, so this is what we call a race condition, where because of the way processes interleave, the correctness of the data can be undermined. Okay, so we need to take care of this. Okay, so this example in the code, all right, where we have. Okay, so and just again, the poll is always there. If you have questions, you can put in the poll. Alright, so here we have two functions, okay, function A, function B, and both of them are tied to two specific threads. So we have function A, okay, that is a task that is running, and function B as well. There's also another task that is running. Okay, and both of them call a common function, increment k, which accesses a global variable. Okay, k equals to k, and it increments the value of k by 1. Alright, so this is what we currently have. Very simple code with two tasks, both having access to a common function with a shared variable. So what is the issue? The issue is k equals to k plus 1 can never be done as a single atomic operation, okay, in a RISC-based system. Okay, why? Because in a RISC-based system, all your execution has to be done by internal registers. Okay, you cannot directly execute or modify content in memory. Okay, which means that when I declare a variable k, okay, k is somewhere in my memories. Okay, and when I want to execute this statement, k equals to k plus 1, I need to do 3 separate steps at the assembly language level. That means at the processor level. Okay, the first step is what we call a load. Okay, I need to load to my internal register. Okay, I say I load to my internal register R7. Okay, once I load to my internal register, then I can perform the computation. Okay, which is through the ALU. Okay, so through the ALU, I perform the add operation with 1. Then I get the result, and then I need to do a store. Okay, so technically, when I execute this statement, k equals to k plus 1, I will need to perform 3 steps. Okay, a load, an increment, and a store. Okay, which means that when we talk about context switching is happening at this level, assembly language level. Okay, because that is the level at which the processor is executing instruction. Okay, what we write at a high level C is only what we see, correct? It's very high level, but when we compile it and it goes in assembly language, the context switching can happen at any of these assembly language lines. Alright, so let's look at what can happen. So if a very simple system, there is no multi-threading, then there is no issue. Alright, a single task, okay, I take a value of k, I increment, so 0, I increment become 1, I write back, so become 1. Okay, so in a simple single-threaded system, okay, there is no issue. Alright, if I have this current code, okay, where two threads are calling increment k concurrently, what can happen? Okay, so what we expect is k to be 0 initially, and when I complete both the tasks, running one time each, I should get k equals to 2. Okay, that is the expected behavior. Okay, but let's see what can happen. Alright, so initially k can be 0, then I load 0 here. Alright, and then I increment, so become 1. Okay, after increment, I write the value, then 1 comes here, correct? Then I switch to task 2. So 1 is loaded, I increment, become 2, and then I write back, so 1 and then become 2. So this is, everybody is happy, correct? What you expected and what you observe is the same. Okay, so you are fine with it. Okay, so this is one possible scenario. Okay, but what if something else happens? Okay, that means I start with 0, I load my current value 0, and I increment become 1. Okay, but before I write back, I have a context switch. Okay, I have a context switch and I switch to task 2. So what happened? When I load, I am still loading 0, correct? Because the k is still 0. So 0 will come here. Okay, and increment become 1, and 1 will be returned back. Then before I write back, I switch back to task 1. Okay, and task 1 will do the store, which is 1. Correct? And then I context switch back to task 2, and again our update become 1. Okay, so both the tasks have run, and both of them have incremented k, but eventually I only see 0 become 1. Okay, instead of 2, because of the context switch that happened, okay, between both of them while this was happening at the assembly language level. Alright, so this is an unexpected result. Alright, and this is the issue. Okay, the results are incorrect only sometimes. Okay, so when you are developing something, okay, you will have some software bugs or hardware bugs, okay, and trying to debug what's happening, correct? And what is the best kind of bug to have? The best kind of a fault or a bug to have is something that always happens. If your system always fails, you should be very happy. Okay, why you should be very happy? Because if it always fails, that means the failure is consistent. If it's consistent means I can debug to find what is the problem. Okay, the one that causes the most headache is the one that happens once a while. Okay, if it happens once a while, it's very, very difficult to troubleshoot because you do not know where to start. Correct? If it happens consistently, if every time I press this button, the system crashes, you know that something is related there. Correct? I can troubleshoot, okay, maybe the button hardware, the ISR, something. So there is a point of entry where I can start to troubleshoot to find. Okay, the most difficult challenges are the ones that your system is running, after 1 hour the system crash. After 1 day the system crash. You really do not know where to start. Okay, because you're trying to think where could the fault be, because it's working what? Correct, it's working and suddenly it fails. Okay, so when results are incorrect only sometimes, it's very, very difficult to troubleshoot. Okay, and usually it's these kind of things that you have overlooked. Okay, somewhere some shared memory is overwritten, okay, something you did not take care and so on. Okay, so ideally we should eliminate this kind of race condition from the very beginning. Okay, so how can I do that? Alright, so what we do is we define a critical section in the code. What is a critical section? It is any section in the code, okay, where you have access to shared resource. Okay, why is this important? Because as long as the resource is shared, then it can lead to a race condition, as we saw just now. Okay, so I want to be able to protect my access to these shared resources. Protect my access to these shared resources, okay, in a proper way. Okay, how can I do that? Alright, so that is basically what we call mutual exclusion, or in short form we call it mutex in the OS. Okay. So using mutex, alright, it is a OS-based kernel call that we can use, alright, to protect access to shared resources. And what it does is it enforces to ensure that only the thread that has this mutex is able to continue execution, alright, and anybody else who does not have the mutex has to wait. Okay, it is like a lock and key mechanism. Okay, that means if I want to access something, I take the key for it and unlock it. So it is mine, correct? And since I have the key, nobody else can use it. Alright, only when I finish, then I unlock and I can pass the key to somebody else. Okay, then the next person who has the key can use it. Alright, so that is the idea behind it. So this whole thing is managed by the OS, but we need to follow the rules of how to do it. Okay, and at the same time, we also need to make sure that there is no deadlock or starvation, which what it means, we will look at it later. Okay, so what is the whole idea behind the mutex? Alright, so if, coming back to the same idea, I have a shared resource, alright, and in this case the shared resource or the critical section is this increment k function. Okay, because the shared resource is the k variable, correct? Okay, so I want to protect access to this shared resource or shared variable. So what must I do? That means before I access this shared resource, I must call mutex lock. Okay, so again the terminology may change when you look at other OS. In some other OS, they will call it mutex acquire. Okay, they will call it mutex acquire, mutex lock. Okay, but it's the same thing. That means you take it, you take the mutex, you take the lock. Alright, once I have the lock, then I am able to access my critical section, and when I finish with my critical section, I say mutex release. Okay, so that is the proper way of controlling access. So now, how does this help? How does this help? That means when thread B, okay, also wants to access the shared resource, you must follow the same rule. Alright, that means I must lock, okay, access K, and then I must release. Okay, now in this example, if thread A run first and it already acquire the lock. Okay, it already acquired the lock. Okay, so if I draw the timeline, thread A and thread B. Okay, so task A is running, it says lock. Correct? Okay, so once it locks, it runs and acquires the mutex. Then halfway through there's a context switch, correct? And then task B try to run. When task B try to run, it will also call lock, correct? Because it also wants to access the k variable. But when you try to access the k variable, what happened? Okay, I mean you try to lock the mutex, what happened? It cannot lock it because somebody else took it already. Okay, so the OS will manage this for us. Okay, the OS will manage this for us to ensure that only one person has access to the mutex at any point of time. So since task A already locked the mutex, now task B trying to lock the mutex, it cannot lock it. So what will it do? It will go to a block state. So this ensures that task B cannot continue and take the k variable. Okay, it ensures that task B cannot continue and take the k variable. Alright, so when can task B continue? Alright, so eventually, so in this case, if it's only two tasks, then once task B go to block, I may be able to context switch back and I can continue with task A, correct? Okay, and at some point of time, I finish with my k variable and then I say unlock. Okay, once I unlock or release the mutex, the OS comes in again and says, okay, who was waiting for the mutex? Task B was waiting for the mutex, correct? Okay, task B was waiting for the mutex, so I will automatically allocate task B to the, automatically allocate the mutex to task B. So once I allocate the mutex to task B, what will the state change be? Block to what? Ready, correct? Okay, block to ready, then eventually it will run, correct? It may not run immediately, but eventually it will run. And once it runs, it has the mutex, it can now use K. Okay, so this ensures that once you enforce this rule in place, okay, then whoever is the first to get the mutex will hold the mutex to modify the shared variable, and when I release the mutex, then the next person in line can use it. Okay, so this is a mechanism that the OS provides us to protect access to shared variable. Alright, so this is something that you must use as long as you have a shared variable among different tasks in the system. Okay, so how to the routines and all later we will go through when I demo the code. Okay, but basically you need to create a mutex. Okay, using mutex ID type. Okay, then you create a new mutex by calling OS mutex new. Okay, if you stick with the default parameters, then you say null. Okay, as a parameter. If you stick with the default attributes, then you don't need to change anything. So you say null. Okay, if you want to change any attributes, then you can pass in the parameter here. Okay, so to lock and release, you say OS mutex acquire and OS mutex release. Okay, so these are the basic functions of the mutex. Okay, now there is another mechanism also provided by the OS. Okay, so one is mutex. Okay, the other one is what we call the semaphore. Alright, and a semaphore is used to manage resource allocation. Okay, resource allocation. Okay, and in some cases you may also use it to synchronize the behavior. Okay, to synchronize the behavior of or the flow of tasks. Okay, so there are a lot of different options. A lot of different options that we will cover this week and next week. So semaphore is one. The next week we will look at events, flags, message queue, and so on. All right. So once you learn all of this, then you decide how you want to come up with the architecture for your project. Okay. So what is semaphore? So semaphore allows you to have control over a bunch of resources. Okay, so one of it is you acquire the semaphore, next is you release the semaphore. Okay, so P is to acquire, okay, and this is to release. Okay, so what do you mean by acquire and release? Alright, so let's look at the example. Instead of looking at all this text, let's look at example. So let's say I have 3 resources. Now what do you mean by 3 resources? Okay, so in a sense, you can think of resources as anything that a task may want to use. Okay, so you can think of it as maybe you set aside certain blocks of memory. Okay, so 1 kilobytes of memory space you set aside. So you have 3 chunks of this. Or you can say I have 3 different timer blocks. Okay, whoever wants to use the timer can use the timer. Or 3 different ADC channel. Whoever wants to do ADC operation can request for a channel. Okay, so a resource is anything that can be shared among different processors. Okay, that you want to manage. Okay, so how can I manage this? So if I say that my S is 3, that means my initial starting point is I have 3 resources. Okay, so whoever wants to get a resource will take the resource. So P is to acquire the semaphore. Alright, so when I want a resource, okay, let's say I have 3 chunks of memory and I want 1 chunk of memory for myself right now, I say P, which is to take the semaphore. So when I take the semaphore, I am allocated 1 chunk or 1 resource. Alright, then another task comes along. It says, hey, I also want a chunk of memory. Okay, so that is also allocated. So the count goes down. So every time you take one of the resource, the available count goes down. Okay, then one of the tasks that acquired it releases it. So hey, I'm done with it. Okay, so I'm done. So it's now available, correct? So the count goes up again to 2. Okay, then another task comes along, say I want. So I allocate again. Then another task comes along and again I say I want. So I'm done. Alright, so right now what happened? Your resource count is 0. Okay, so you all had 3 resources and now 3 tasks have already acquired these resources. Okay, and as far as the semaphore is concerned, the count is 0. Okay, the count is 0. Now, once the count is 0, another task comes along and says, I want this resource. But now you don't have any more resource to give. Correct? You don't have any more resource to give. So what happens? I am blocked and I'm put in the queue. Okay, I am blocked and I'm put in the queue. Alright, so this process X is now going to be in the queue. Okay, it wants the resource, but I cannot continue without the resource. So because of that, I am put in the queue. And another task comes along, Y, also wants the resource but don't have. So again, I am blocked and I am put in the queue. Alright, so now all three resources are occupied and I have two tasks in the queue. Alright, so X and Y cannot continue unless somebody releases the resource, correct? Okay, until somebody releases the resource. So when somebody releases it, then I am able to unblock and allow X to be out of the queue. Alright, so I'll unblock process X when somebody releases. Okay, but as again you can see that in this case, when I unblock, the count never go up. It still stays at 0, correct? Okay, why? Because the moment I release, somebody take. Okay, the moment I release, somebody take. So the count sort of temporarily go back to 1, but eventually go back to 0 again. Alright, so the count still stay at 0. Okay, then again when somebody else release, again the count still stay at 0 because somebody else is in the queue. And Y is in the queue. So the moment one of the tasks release, I straight away allocate to Y. Okay, so again the count stay at 0 and I allow Y to continue. Okay, then eventually when nobody is in the queue and I am releasing it, then the count goes back up again. Alright, so resource management, okay, by semaphore is one way you can use, okay, if you want to be able to define who can define some resources that can be shared. Alright, so how do I create a new semaphore? Okay, there's OS semaphore new function, okay, which I can create, alright, where I can specify the max count and initial count. Okay, so max count means what's the maximum number of resources and what is the initial count. Alright, now in most cases you may say, shouldn't the max count and initial count be the same? Alright, because if I'm creating a new semaphore, if I have two resources, then I should initially have two resources, correct? Alright, but okay, you may want to play around with this later, okay, which I will show later, how you can use this as a way of synchronizing. Okay, so you can also use semaphore to synchronize some behavior of different threads, which on playing around with how we use the initial count. Alright, so to acquire the semaphore, okay, to acquire the semaphore, you say OS semaphore acquire, okay, which is this function. So I pass in the semaphore ID, alright, and when I finish, I must release the semaphore. Okay, so now you can see that in this example, I use semaphore in a similar context as mutex, correct? Okay, because mutex also we did a similar thing. Alright, we say that before I access this shared resource, so in this case the shared resource is the LED. So before I control the LED, I acquire the semaphore. When I finish, I release. Okay, the same thing for the green LED. Before I use, I acquire. After that, I release. So it looks to be the same. Okay, so you can sort of use it in a similar fashion. Alright, because if I declare it as a max count of 1, okay, that means if there's only one semaphore, in a sense, you call it a binary semaphore. Okay, and that behaves in a sense similar to mutex. Okay, but there is a very important difference. Okay, there's a very important difference which we will cover next week's lecture. Okay, but you can sort of use it in a similar context. So in this example, it behaves in the same way like how the mutex behave. Okay, so I lock it or I acquire it, I control the shared resource, then I release it after that. Okay, so a mutex and semaphore. Okay, again, like I said, a mutex is specifically to have mutual access to a shared resource or a shared object. Okay, it is similar to a binary semaphore, but what is the important thing? Okay, mutex has this very important property called priority inheritance. Okay, which we will cover at a later time. Alright, but this important property, priority inheritance, is very critical. Okay, mutex has it and semaphore does not have it. Okay, so that is why you need to use mutex exclusively for shared resources or critical section. Alright, and to manage multiple resources, you can use semaphore. Okay, and at the same time, okay, one of the things that you can use semaphore for is also for synchronizing. That means I can allow one task to signal another task, okay, through semaphore. Okay, so that is one way I can say that, okay, a particular event has happened. Alright, so what an example is, for example, task 1 is running. Okay, so let's just say that your task 1 is running, or your, to put it simply, maybe you say that, okay, my motor is running. Okay, at some point of time, I want to wait until the sensor is triggered. Okay, so let's say I run my motor until maybe I have a sensor at the front, and I want to keep running until the sensor is triggered. How do I know the sensor is triggered? Okay, so I can say that until here I say OS SEM acquire. Okay, I call OS SEM acquire, but my initial count is 0. So if my initial count is 0 and I call OS SEM acquire, what will happen? I will block, correct? So I can say that if I am blocked, okay, then I stop the motor or something like that. Alright, then when task 2 is running, at some point of time it triggered a sensor, correct? And when I trigger the sensor, then I say OS SEM release. Okay, so when the semaphore is released, what will happen? Whoever is waiting for it will be unblocked, correct? Okay, so this will allow the OS to send a signal to task 1 that this event has happened. The sensor has been triggered. Okay, so because the sensor has been triggered, the task 1, which was originally blocked, is now unblocked and now can continue. Alright, so this is a way of what you call synchronizing or managing the flow of different tasks. Okay, so this is only one way. We will also cover other ways later on. Okay. Alright, so just now we talk about deadlock. Okay, so what is a deadlock? Okay, so a deadlock is where everybody is waiting for each other. Okay, like what happens when you and your friend are doing a project together, so right? Your friend asks you for his code, you asking for his code, and both of you wait for each other to pass the code to each other, correct? And nothing gets done. Alright, so that is what we mean by deadlock, and nobody wants to do anything. Okay, so that is a deadlock situation. So how can we have a deadlock situation? Okay, so let's say I have task A and task B. Okay, so let's draw a timeline, and let's just say that both task A and task B have two shared resources, R1 and R2. So both task A and task B both need resource 1 and resource 2. Okay, so let's look at this scenario. Task A runs and it acquires resource 1. Correct? Okay, then after a while there is a context switch. Okay, then task B runs. Alright, and task B runs, it acquires resource 2. Okay, then after a while there's a context switch. Now what happened? I say I want resource 2 now, correct? Because I want resource 1 and resource 2 to continue to run. But what happened now? Resource 2 is held by task B. Correct? So what will happen? At this point of time, I'll go to a block state. Okay? And since task A is blocked, I can do a context switch, and task B run, and then task B say, hey, I want resource 1 now. But resource 1 is held by task A. But task A is blocked. And now you are also going to be blocked. Then the whole system just hang there until the battery run out or crash and burn, correct? Okay? So that is what we call a deadlock, correct? Because now what will happen is, both of them will become blocked indefinitely. Correct? Because task A wants something that task B has, task B wants something that task A has. But the problem is, both of them are blocked, correct? And there's no way for them to release the resource that they have. Okay, so this is what we call a deadlock situation. Alright, now, how can I solve this? How can I solve this? Alright, so I mean, there are many ideas out there, but it's actually a very, very simple solution. The very simple solution is, if I have multiple resources, I just ensure that I acquire the resources in the same order. Okay, if I acquire resources in the same order, I won't have this problem. Okay, so what do I mean by that? Okay, so again the same thing, task A, task B. So task A run first, it acquire resource 1 and then context switch, correct? And since I'm going in the order of resource 1 and resource 2, task B must also ask for resource 1 first. Okay, so the moment I cannot get the first resource, that means somebody else already had the first resource, correct? Okay, so I will immediately go to a block state. So I'll go to a block state, which means that task A can continue, it can take resource 2, and then when I eventually finish, I release, correct? I release R1 and R2. Then task B can happily continue, correct? Task B can acquire resource 1, then it can acquire resource 2, and it can continue. Okay, so a deadlock can be easily solved by just enforcing that all the resources are acquired in the same order. Okay, so whoever happens to take the first resource will sort of continue until they finish. And then there is no deadlock situation. Okay, so again, when will you have deadlock situation? Okay, when you have mutex, okay, but you're holding on to the resource and you want additional resources that someone else has. Okay, so again, it's a kind of a circular wait or circular dependency, because I wait for you, you wait for me, and so on. Okay, so that is the condition for deadlock. Okay, so before we end, before I go for the break, so now we are doing multi-threading, we are learning about all this. But you have actually seen multi-threading before, in your year 1. Do you remember when? In your year 1, you see multi-threading before. Okay, so let me show you the code. Maybe it brings back a lot of good memories or nightmares. You don't remember this? This is from your EPP2 code, your RPi. Okay, so like I said, either it brings back good memories or brings back nightmare. Okay, so this is actually from your RPi code. Okay, and if your RPi code, if you remember, it communicates with your Arduino Uno, correct? On the Uno, what do we have? We have interrupt for transmit and receive, correct? On the serial interface, we have interrupt for transmit and receive. But on RPi, we don't have interrupt. But now, how did the transmit and receive happen concurrently? It happened concurrently. And if you look down here, this is your reading, correct? It's your get char. Okay? This is your reading and writing back. So this is your transmit, and this is your receive. Alright? Okay? And both of them are actually happening concurrently because in your Linux operating system, you use fork to spawn a process. So your transmit and receive is actually happening concurrently on the RPi. Okay, it's actually happening concurrently on the RPi. Only thing at the time, we never go into all this detail. Okay, but that's why your RPi can also transmit and receive at the same time, even though we never use interrupt, because it's actually running on 2 separate tasks. Okay, so in the Linux operating system, you use fork. When you use fork, you can fork out the one brace to another brace. So that means this will run on one task. This will run on one task, and this will run on another task. Okay, so we actually did do this before, only thing at that time we never go into this detail. Alright, but if you look back at your code, you will see this. Okay, so before I go for a break, life hack. So I want to share this nice message I received from one of our graduates. Okay, so he graduated last year, he's currently in Oxford, okay, doing MSc Advanced Computer Science. Okay, and so like for him, I have written referral letters for a lot of students, NOC, SCP, after graduate, for many years I've been writing. Alright, so until now also I've been writing. Okay, people always ask me, Mr. Habib, please help me write. Okay, I want to go NOC. Okay, can. I want to go SCP, also can. I'm going for internship, also can. Alright, okay, so if you want referral letter, can, I'll definitely do for you. Alright, no problem. But what you must give me is, you must be very thick-skinned. You must write very nicely about yourself. Alright, so even if you write 2 lines of code, you say, I wrote 10,000 lines of code in this project. My friend just do iPower only. Okay, so you must write very, very nice things about yourself. Okay, or what you have achieved, what you have accomplished. And you should not focus on what you do here in your curriculum. Okay, you must talk about things that you have done outside of the curriculum. That means you take part in hackathon, or you did some project in the internship, or something else that you have done. Okay, so when you have a lot of other things to say about yourself, your application will stand out. Okay, when you apply for something. Alright, so referral letter only works based on how much you have done. Alright, so if you have plans to do anything, whether it's NOC or whatever, or even when you want to graduate, okay, your profile, you must try to boost it up by doing a lot of other stuff. Okay, so of course, term time everybody is busy. Everybody is busy, so you don't have time. But during the vacation time, okay, try to see what you can do to boost your profile. So when you boost your profile, then I think you stand a better chance, okay, of getting what you want. Whether it's your job you're looking for, or some NOC or internship or anything like that. Alright, so I'm always ready to help. You just reach out to me, I'll help you, no problem. Okay, so that's it for the material. We'll go for a break, and after that we will come and look at the code, okay, and discuss some of the behavior of mutex and semaphore. Okay, so now it's 10:55. Okay, we'll come back at 11:10. Okay, 15 minutes. 11:10 we come back, and then we will go through the code. Only when resource become available. Okay, so let's review the mutex and semaphore code so you understand some important concepts. Okay, so for mutex, again you can go back to your website, alright, and go to the mutex link to understand the kernel calls, alright. So to create a mutex, we call OS mutex new. Okay, we need to first create a mutex ID type. Okay, OS mutex new, alright, and that is inside your main function here, alright, where you create a OS mutex new. Okay, so this is your OS mutex new over here. Alright, once you have created a new mutex, okay, we can use it to control access to a shared resource. So in this case, the shared resource is your LED, RGB LED. Alright, so previously we saw that, okay, when I write the LED control function, alright, both the tasks are running concurrently, but now I'm going to use US mutex acquire to lock my access here. Okay, so before I acquire the shared resource, I acquire it and then I release it. Okay, same thing over here, I acquire and then I release. Okay, so in this example, the shared resource that we're talking about is actually the LED. Okay, so this is the code. Let me run it first. Okay, to confirm our behavior, and then subsequently we can okay, so if I run this code now, you will see there is red, followed by green, followed by red, and so on. Okay, so what is happening? Okay, so I have my red LED, okay, LED red thread that is running, okay, and I have my LED green. Okay, so who will run first? My red will run first, correct? Because I created the red thread first. And then the first thing I do is I say mutex acquire. So I basically lock my mutex, correct? I lock my mutex before I do anything else, which is access my shared resource. So after that I do my LED control, which is on. Okay, and after that I say delay. So we know that at this point of time there can be a transition. Alright, so the green that was waiting all the while will now become ready. I mean all the while it was ready, and now it transitioned to run. Okay, when it transition to run, the first thing it tried to do is what? The first thing it tried to do is it tried to acquire the mutex, correct? Okay, the very first thing it tried to do is it tried to do this. It tried to acquire the mutex. Okay, but what happened? The mutex was already locked by the LED red. So since I cannot acquire the mutex, which means I cannot access the shared resource, which is in this case the RGB LED. Okay, so this will cause me to immediately transition to block state. Okay, so I will transition to block state, which means that since there is nobody else, I will transition back. Okay, and then over here, again I will do the off. Okay, and then I'll do the delay, and then finally I will release the mutex. Alright, when the LED red release the mutex, the OS will know that somebody else is already blocked waiting for the mutex. Okay, which means that it will now allocate this mutex to the green LED thread. Okay, which means that at this point of time I will be able to become transition to ready state. So I'll unblock and I can transition to ready the moment the mutex was released and handed to me. Okay. Now when the LED red thread runs, what happens? It also it goes and it switches. It already acquired the mutex, correct? So in this case, it considered it already performed the lock operation here. Okay, because it previously tried to lock but couldn't lock. So the moment the mutex was allocated to it, it's considered already locked the mutex. So once it locked the mutex, I can on. Okay, and then I will delay. Okay, now when I delay, what happened? I transition back to red, correct? Okay, when I delay, I'm actually transitioning back to red. So at this point of time, I'm transitioning back to red. But in red, what am I doing? I have already finished one iteration of the loop. Okay, I already released the mutex and now I'm going back to acquire one more time, correct? Okay, and when I try to acquire one more time, what happened? I will now try to say lock, but I cannot lock, which means now I will go to a block state. So each point of time, each iteration, I try to acquire the mutex, but I cannot acquire if somebody else has it, so I block. Until the other thread completes and releases the mutex, then I unblock. Okay, but while I'm using the other thread, loop back and try to lock again, correct? And cannot, so it will be locked waiting until my current task finish. Okay, so that is why you are able to observe the red and green separately. Okay, so the red acquire first, when it finish, then green. Okay, but while red acquire, green tried to acquire, but got blocked. Okay, only at the point when the red release, okay, finish one iteration, release, then the green was able to be allocated and it unblocked. Then it continues. Okay, so you must understand the sequence. Don't just see red, green, red, green. You must understand that this is what is happening. Okay, all these things are actually happening in the background. Okay, who is trying to lock, who is blocked, who is ready, who is running. Now all these things are happening in the background for us to observe this behavior. Okay, so this part we are clear, correct? This part we are clear because it reinforces what we just discussed, that the mutex is locking access to a shared resource, which is the LED. Okay, now let's experiment a bit. Let's experiment a bit to change something, to change the behavior. So we know that both the red LED thread and the green LED thread are accessing a shared resource, and the rule is simple. If I'm accessing a shared resource, I lock the mutex, access the shared resource, and release the mutex. Okay, it's fine. Okay, so if you are writing the code, no problem. You are writing the code, you know the rule, you follow. But in the project, what's happening? You are working with your friends, correct? So on that day, your friend not happy with you. Say, I don't want to follow your rule. Your mutex is your problem, not my problem. Correct? Then you say, oh, your LED red thread, you follow the rule. I am doing green thread, I don't want to follow your rule. So I don't use mutex. Then what will happen? So the LED red thread is following the rules, correct? It's following the way it should be done, which is I lock the mutex, control access to a shared variable, and release the mutex. Okay? For the green LED, I don't want to follow the rule. Correct? I want to break the rule. I just want to control the LED. Okay? So what will happen? What do you think? Will it be only red? What do you think will happen? Okay, so it could be that only red runs, correct? Because red is following the rules. Okay? Or only green runs, or both will run, or nobody runs. Okay? So all this is important. So these are the kind of things you will see in the exam. Okay, so I will release practice question for the exam. So exam is, I will discuss the format all later, but you will have a lot of code analysis to do. Okay, which means I'll give you this kind of scenario, and then you must tell me what will happen. Okay, so what will happen? Okay, so let's just see. So you observe as yellow, correct? Which means red and green running together. So what does this tell us? It tells us something very, very important. And what is the very, very important thing? The idea that the mutex is tied to the LED is only in your mind. The OS does not know why you create a mutex. Okay, this is very important. When you create the mutex, only you know why you create the mutex. In your mind, you decided that the mutex is tied to the LED. Okay, so when you use the mutex, the OS just follow the rule. What is the rule? If you try to lock, if it's available, you can lock, you can continue. If you try to lock and it's not available, you cannot continue. That's the rule. Simple. But what is it for, why you want to use it does not know. So only you know that you're supposed to use it for the LED. So this is a very important thing because it's very easy to make this mistake where your friend create a mutex and you don't follow the rule and you don't use the mutex. Okay? So in this case, what is happening? When the green LED runs, okay, in this case when the green LED runs, okay, what happens is I actually I'm able to do some transition here, okay, and since I don't follow the rules, I can straight away go and on. Because the green thread is just running code, it never asks for mutex. Okay, so there is no reason for it to be blocked. Okay, so the green thread will, when it runs, since there is no mutex acquire, mutex release, it will run by itself, okay, without anybody stopping it. So it will just go on, delay, off, delay, and so on. Okay, so this is very important. So you must be clear that the mutex is the idea. You're using a mutex for what it provides. It provides you the ability to say that if I try to lock and if it's available, I can proceed. If it's not available, I will block. Okay, and if you use it correctly, it works. Okay, this is an example of where one thread used it correctly and another thread did not follow the rules. Okay, and that's where you have unexpected behavior. Okay, now let's do something else. Okay, so now you have another friend in your team, say that I fight with you only a bit, so I follow half your rule. Half your rule means what? I take but I don't give you. Okay, so another of your teammate not happy with you fully but happy with you half. Correct? So you say I follow half of your rule. Okay, you want the mutex, I acquire the mutex but I don't want to release the mutex. Then what will happen? Think about it, what will happen? Red will run, then green will run, then red will run, then what is going to happen? Okay, so let's see, then let's think about what we observe. Okay, red, green, and nothing else. Nothing else. You only saw one red and you saw one green and nothing else. Okay, so this is important. So what is actually happening? Okay, so if you come back here, what we have done is we have removed this. Alright. So what is happening? Your red acquires the mutex, controls the LED. Okay? So all of this will now behave as per normal. That means you try to lock it, okay, but you don't get it, so you are blocked. Correct? You are blocked. Okay? Until a point of time when your contact switch here happen. Okay? So initially we see the red, correct? This is the first red that we observe. Then your green try to lock, cannot lock. Then you switch back to red. Okay, so you have your off, Okay, then you have your delay again. Okay, and then you release. Alright, when I release, then what happens? Then that is the time when my transition can happen. So over here, I will go to unblock. Okay, then I will be able to on. So I already locked the mutex here and I on, correct? So again, I go through the whole cycle. So delay, then off, then delay. Okay, so this is the green we observe. Okay, but sorry, I on, delay, yeah, off, delay, but then I don't release the mutex, correct? I don't release the mutex. So while this was happening, alright, I actually have a contact switch here trying to lock the mutex, correct? I already have a contact switch trying to lock the mutex, but I was not able to lock, so I'm in a block state. Okay, so I'm in a block state here. Alright, so if I'm in a block state, I can only unblock when somebody releases the mutex, correct? Okay, I can only unblock when somebody releases the mutex. But did green release the mutex? No. Okay, what is this? Okay, so if green did not release the mutex, I will be forever blocked, correct? Okay, now when green finishes one iteration, it never released the mutex, so this is not there, but I go back and I try to acquire again, correct? Okay, now this is the thing. So sometimes you may think, but I am the one who acquired the mutex, what? Shouldn't I be allowed to continue? You can continue, but you go and ask for it again, what? Correct? You ask for it again means it will try to see whether it is still available. So as far as concerned, it's not available. Correct? Because it's already been acquired. So even though you are the one who acquired it last, but you try to acquire it one more time. Okay, you try to acquire it one more time, which it will not allow. Alright, that is why even though you go back in and you try to say, I acquire one more time. So here you try to lock one more time. Okay, but it will not allow you to do it, so you will become blocked all the way. Okay, so eventually both the tasks remain blocked indefinitely. Both the tasks remain blocked indefinitely, and that's why you do not see any other LED behavior. Okay, so that is the mutex. Okay, so you can see that you can have a few different scenarios even with mutex. Okay, if you use it correctly, okay, or if you use it incorrectly. Okay, with one task totally not using the mutex, or using the mutex partially, using it partially. Okay, so that is mutex. Okay, now let me just show you the semaphore also, so you understand how the semaphore concept works. Okay, so let me show you this one first. Okay, so let's look at a semaphore code. So I'm creating a binary semaphore. So again, for now, look at this line. So I'm including this line, semaphore 1, 1, which means that the initial count is 1. Okay, max count and initial count is both 1 and 1. Okay, max count is 1, initial count is 1. And both of them will acquire and release the semaphore. Okay, so both of them will acquire the semaphore and release the semaphore. Okay, I will acquire and then I will release. Okay, so this is the binary semaphore, which technically will behave like a mutex. I will behave like a mutex. Okay, so if I build this code, okay, so you see red, green, red, green. So it behaves in a similar fashion. Okay, it behaves in a similar fashion. So like I said, a binary semaphore and a mutex has a similar behavior. Okay, now let's make some changes. Okay, let's make some changes to the code. Now instead of creating with initial count of 1, I'm going to create with initial count of 0. So initial count is 0 means whoever tried to acquire will become blocked, correct? If my initial count is 0, okay, if this initial count is 0 over here, okay, that means whoever tried to acquire will become blocked. Okay, because there's no semaphore available. Alright, and what have I done here? Okay, so let me copy that code over here. Okay, so over here I have configured my port D IRQ handler, which is my push button. Okay, and what does the push button do? The push button, whenever I press, I will release a semaphore. So think about it. So initially a semaphore count is 0, correct? Okay, so when initially a semaphore count is 0, when I run, what will happen? Both LED track will try to acquire, LED green will also try to acquire, and both will become blocked, correct? Okay, so let's draw it out here. Okay, so I have my red. Okay, so the first thing I try to do is I say acquire and then I become blocked. Okay, and the green thread also the same thing. Okay, it initially tried to acquire and I cannot acquire, so I become blocked. Alright, so that is the initial situation, because both of them, the first thing they do is try to acquire semaphore. Okay, and since there is no semaphore available, both will become blocked. Okay, and how do I unblock one of them? I use my push button. Okay, so whenever I press my push button, okay, I will release a semaphore. Okay, I'll release a semaphore. Okay, so let's see what happens. So I'll download this code. Okay, so when I run the code, you can see initially there is no LED. No LED lighted up because currently both the tasks are in a block state. Okay, now when I press a button, the LED light up, correct? Okay, now when I press again, Where is it? Oh, okay. I must not release the semaphore here, my fault. Okay, so the semaphore release must only come from the IRQ handler. Okay, so you can see initially there is no LED. Now when I press the switch for the one time, the red LED light up. Okay, when I press again, the green LED light up. Okay, then when I press again, the red LED light up. So basically what's happening? Whenever I press the switch, okay, whenever I press the switch, I am releasing a semaphore, correct? Okay, when I release a semaphore, whoever is the first in the queue will get it, correct? Okay, so since the blue one was the first in the queue, I will get it, so I will go through the whole sequence, okay, of on, off, okay, on, delay, off, delay, correct? And then once I finish, I go back to the beginning of the loop again, which means I will try to do a acquire, correct? Alright, but now I'm second in the queue, alright, because green is already the first in the queue. Correct, green is already trying to acquire and first in the queue. So the second time that I press, what happened? I will allow green to get it. Then again red will get it, and then green will get it, and so on. Okay, now if I press very fast, what happens? Red and yellow, do you see? If I press very fast, it will become green then yellow. That means when green release and on, I release again. So red also can unblock. Okay, so this is a way of synchronizing or controlling the behavior of when some task should run. So I can say the task block, wait for semaphore. Then when task A finish something, I release a semaphore, task B continue. And task B finish something, task A continue, or task C continue. Okay, so semaphore provide you with one option of synchronizing the behavior of multiple tasks. Alright, again, it is just one option. We will explore a lot of other options, events, flags, message queue, and so on next week. Okay, so for now, just we understand this first. You go and try it out in the labs, see how everything works. Then next week when we cover event flags and message queue everything, then you will get a bigger picture of how I can frame my whole architecture. Okay, then everything will become easier. Alright, so again, try to speed up your project work and make sure everything is in place, all your device drivers, all your hardware. Okay, so within these 2 weeks when the OS architecture is clear to you, then you just put everything together and it will work. Can? Okay? Alright, so if you have any questions, you can ask me. If not, thank you. I will see you all next week. Okay?